Okay, so if we find the second derivative of this function, this will be this value, and then in order to find out the average derivative of this function, we will integrate this, and then we will divide by b minus a, as I have explained you in this equation here. So we will now, this is actually, we want the second average derivative. We will integrate from a to b, and then we divide, then we will get the mean second derivative of that function. So we have the second derivative, and this is the integration, and we now need this average derivative, average f double dash x. So how we can get it? The integration from, so I have already found the integration here, so just let me put the values here. So 0.8 minus plus 2 0.8 plus 2025 multiplied by p square minus 3600 multiplied by this to the power 3 plus 2000 multiplied by p raised to the power 4, so whole divided by b minus a, which is 0.8. There is no need to put the values for 0, because if we put the values 0 here, so all these things will become 0, so that's why there is no need for that, and we have minus 60. Now we can find the error because of this trapezoidal rule, and this error is, this is the second derivative multiplied by interval b minus a divided by 12. So let's find out the ET, the truncation error. So it will be equal to 1 over 12 minus 1 over 12 multiplied by second derivative multiplied by b minus a, which is actually 0.8 cube. So let me check here. Yeah, b minus a cube, and this is this true error. Not true, it's the truncation error. So but this is actually, you can see here, it's still a huge difference, and we cannot find out even the value of the truncation error itself is not correct. So these are the limitations of the trapezoidal rule. But let's go for the next thing, how we can make it more accurate, which is actually the multiple application of trapezoidal rule. So what is this multiple application of trapezoidal rule? We have function. So what we do, we divide that function into different parts, like maybe 3, 4, or 5 parts. For example, if we divide into 3 parts, 1, 2, and 3, for example, then we will find out, I mean, these parts should be equal, and you can get the interval by b minus a over n, where n is the number of parts, and then at each part you can find out the value of the function by putting the corresponding x value. For example, if you put x0, you will get fx0, as we did in the previous example, and if you put x1, you will get fx1, and if you put x2, you will get fx2. So this is the way we actually find out all these points. Once we have all these points, then we apply this formula, this equation, in order to find out the integration, and where n is the total number of points, and the first point is actually starting from 0, and this is the last point. So you can say this is actually f of a, and this is actually f of b. So let's solve one more example, and before moving to the example, this is the equation by which you can find out the error. Again, here this is the second average derivative, but n is the number of segments, and this is the total length of about which you have to find out the integration. So let's solve this example, the same example, but now we actually want to so this is the same example, but now actually we want to solve this example for multiple points. So let's solve this example for let me first crop it. So let's solve this example for multiple points. So this is the example that the function is same, a is 0, b is 0.8, and how many number of segments two segments, so we have to consider actually two segments. So we can say that n is equal to 2. Okay, so and now interval h will be equal to b minus a over 2, so it's actually 0.8 minus 0 over 2, so this is h. So we have how many values? For example, x0 is 0.0, and then x1 is 0.4, and x2 is 0.8. so where this is actually xa, I mean this is corresponding to, you can say, f of a is actually f of x0. So then we can find the values of f of, for example, so how much will be f of a or f of x0 and f of x1 and f of x2. Okay, so we can calculate. I have already done here. So this is the function, control C, control V. Okay, so here instead of D25 I will replace it with C25. Okay, C, 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 and C, and C. Okay, and then I control C, control V here, and then control V here. So these are the values, and now I can apply the trapezoidal rule formula that I have just shown you sometime before this one. So here this is the summation of the values in between these 2 points. For example, now we have just 1 point, so this will be 2 times f of x 1. Okay, this is f of x0 and this is f of x1, because if we have like more segments, then we can have the further input of these values, but at the moment, as there are just 2 segments, we are solving this problem. So how we can find out the integration? The integration is equal to b minus a, which is actually 0.8. okay, I just put the value directly here, 0.8 multiplied by f of, okay, this plus 2 times multiplied by f of x1 plus this value divided by it should be the 2n. okay, so divided by 2 multiplied by n, where n is the 2, so it is actually 1.0688, which is actually pretty close to this value. And you can also estimate the error, like the truncation error, not the true error. So how you can estimate? The formula is here. Okay, so this is the formula: b minus a cube divided by 12n square multiplied by f double dash. Okay, so let's apply this formula here. So minus 1 over 12. So we have already found the every second derivative, and that was minus 60, multiplied by b minus a cube, which is actually 0.8 cube, divided by 2n square, which is actually 2n is 2, so square you can say this is 4, so this is 0.32. okay, yeah, 12, okay, not 2, this is actually 12. okay, so this is here I should just say this is actually 4, so 0.64. so if you add this error into this integral, so you can get a value which is pretty close to this. So this is how actually we can actually if you sum them together, you will get the value somewhere 1.7. so this is how you can find out the find out the integration when there are more than 2 points. So you just see that we have just increased just 1 point, and then we got a solution that is pretty close to the analytical value. The same way you can increase, you can also do this procedure for more number of steps. For example, if you want to repeat the same procedure for more number of steps, we can do that. So let's do it for more number of steps. Say, let's say n is equal to 3. So then this will be h will be equal to 0.267, and then we will be having x0, and then x1, x3, okay, and then this will be 0, okay, and then this will be 0.2667, and this will be equal to this multiplied by 2, and then this will be equal to this multiplied by 3. So this is actually 0.88. okay, so now you can apply the same equation. For example, this is, let me check, okay, it's fine, Control C and then Control V. So, and this is actually fx3. Again, how you can find out the integration? 2 times g37 plus 38 plus this value divided by 2 into n, where n is actually 3. Okay, I think I did some mistake. So this is actually b minus a multiplied by g36 plus 2 times g37 plus g38 plus g39. okay, then this should be, this division should be outside. So this is 1.3693, and the truncation error will be this will be n square, so that is actually 3 square, that is 9. So this is 0.28, and if you see now your answer is 1. If you add them together, you will get like 1.65, and that's pretty close to the true value. So this is n is equal to 3, and the same way you can keep on increasing, and you will get this table, and in this table you can see the true percentage error is keep on reducing and until it become equal to 1.6 once you have the number of points equal to 10. So this trapezoidal rule, in short, we can apply for problems, but the thing is that we should have more number of points in order to get the actual or the or in order to get the value which is very close to the actual or the true value. But if we don't do that, then we have to go for another solution. So this is one more example. You can also solve this example using the trapezoidal rule, but sometime it becomes easier to apply this trapezoidal rule using a computer program, because if the number of points are like, let's say 10 or 12, then I think we need some complicated phenomena or complicated Excel programming in order to solve such problems. So for example, here if it is like if you increase the n, then each time you have to repeat the whole procedure and then you can get the solution. But this is not like you just change the value and you get the answer. But if you want to do that, you can use MATLAB or like some other computer program, Visual Basic, Fortran, C++, and then you can solve the problem by using that code. And such problems are much easier to solve using some codes rather than using the Excel program. Anyways, but you can still use Excel for such problems. Okay, so I was talking about this problem. Okay, yeah, this one. So this is the problem, the same parachuter problem that has been solved in the previous chapters. But in this case, what actually we want to find out the position of this parachuter after a certain period of time. So position means the distance. How we can get that? Actually, we have to integrate this equation with respect to time. So instead of integrating this, we are going to use the trapezoidal rule, and the values of g, c, and m are given here. And if you use the same equation for 10 seconds, because we want to know the position after 10 seconds, this is the actual value from the analytical solution, and this equation gives you the analytical solution. So how you can solve it? You can use the trapezoidal rule. N is the number of segments, 10 segment size is 1 second, and you put this 1 second in this equation, 1 second, and you will get like 10 or 11 points, like starting from 0 to 10. And then if you uh, sum up them up and you apply the trapezoidal rule, you will get this value. And the same thing you will get if you have 20, 50 and more points. But just see here, if you have like 1000 points, then I think it's very hard to use Microsoft Excel. Like you have to calculate 1001 F values or FA or FB values, so this becomes very complicated. But we can solve such problems using a very simple computer code like this. Just we can write few lines, and with the help of these few lines we can solve this type of problem. So the next thing that I'm going to explain you for the integration is the Simpson rule. So again, this is a numerical approach. This is not an accurate method, but in Simpson rule we have actually maybe the first or second or third order polynomial function. We replace the original function not with the trapezoid but with some polynomial, and this polynomial could be a high order polynomial. Okay, and if you use such polynomial, for example, this is your function, this blue line is your function, so you convert that function into a polynomial function, a dashed line, or you can see a dashed line here, and then you simplify this. So what is the result? I'm not going to tell you the derivation. So this is the result, and you can find out the integration of that function by using this equation 21.15, where x1 is actually the value of the function in the midpoint. For example, in the previous example we have a as 0 and b as 0.8, so x1 will be in the mid of these two, that will be 0.4. so the error calculation is pretty similar as like trapezoidal rule, but the only difference is that now we have the average fourth order derivative. So instead of second derivative, we are going to have fourth order derivative, average fourth order derivative of that function, and then we can apply the Simpson 1/3 rule in order to solve this problem. Okay, so let's solve the same problem that we have solved using trapezoidal rule with the help of the Simpson rule. Okay, so this is actually the problem. So we have this example here. So what exactly we need, we want to solve this question with the help of Simpson rule. So let me take the basic data from here. Okay, so we have A, we have B, but we also want to find out the, this is actually f of x1 is actually f of x0 is actually f of A. Okay, and then f of x1 is actually, you can say here that this is actually x0, this is x2, okay, and x1 is in between these two, so the x1 will be equal to 0.4, or you can add here, for example, x1 will be in between these two, this is actually 0.4, this is x2, or you can say this is b. So how you can get fx0, this is the same like f of A okay, let me put here control V and then control V. Okay, so this is f of x 0. Okay, this is fine, and then this is f of A, this is also fine, but this is not f of A, this is f of x1, and then this is f of x2. Okay, so and then